the surface. Near the surface. So check, we're on the surface of Earth. I mentioned when I first introduced this, how close do you have to be to the center? Well, the Earth is very large, so even if you might climb to the top of a hill or fly in an airplane or climb to the top of Mount Everest, that's really not much of a difference. And so this encompassed everyday circumstances. All everyday situations. But what if you went really, really high above the surface of Earth? What would the gravity do then? Well, we don't know. We don't know enough yet, right? This was basically a value that we borrowed before its time because it was a convenient problem to use constant acceleration with. We don't know a lot about how it works. Pretty much the only thing we know is that if you want to talk about gravity, talk about gravity. Don't accidentally mix in something that's due to air resistance, which is completely a different thing, right? That's often a misattribution error that people make. They take something that is due to gravity and air resistance and they think it's gravity, right? So a common mistake that people think a feather falls slower because of somehow gravity, and nothing to do with gravity. It has to do with air resistance, right? When we made sure that this idea that gravity causes constant acceleration to everybody was compatible with Newton's second law, we got basically F equals ma. And this really didn't solve anything. It just made the ideas compatible with Newton's second law. In fact, it really brought up more questions than it answered. Gravity gives everything the same acceleration. Big and small gives everything the same acceleration. And yet, when we studied Newton's second law, we realized that things that have more mass are inherently more stubborn to accelerate. And so we have to conclude that somehow big objects, big mass objects, feel more force. The only way they can accelerate the same is if they feel more force. It's right in the equation. If g is fixed for everybody, if you have more mass, you have to have more force. And so then we ask, well, how does gravity know how to pull harder on things that have more mass? We don't know yet, but it somehow does. Somehow the force of gravity knows to pull harder on things that have more mass to make them accelerate the same as everybody else. So there are obviously a lot of questions here that we have unsolved, and we'll solve them all today. We'll see why all of these features appear in the force of gravity. So let's write down Newton's law of universal gravitation. This is not to be confused with Newton's laws 1, 2, 3. Those are fundamental laws that govern all forces, gravity or not. Newton figured out a lot of stuff, and he also happened to just be sitting around thinking one day and figured out the force of universal gravitation, how gravity works everywhere in the universe. Okay? So, let's write down what that law is. Newton basically said if you have two masses, so we can draw them like that, and he realized that if you have mass, you belong to a special club. And that special club is attracting every other mass in the universe. So if mass is a property you have stuff to you, then you will also be attracted to all other mass. We call that attraction the force of gravity. So gravity is how you interact with other masses. Mass is your intrinsic property, and the force of gravity is what we call your interaction with other masses. The force is, of course, equal and opposite. Newton could use his own third law to say that they pull on each other equally. And he also wrote down the force, the mutual common force of attraction that they feel to each other. And what he supposed is that the force is stronger if one or both masses are bigger. So I'm putting in here m1 times m2. So it's not just if you have mass you belong to this club. The more mass you have, the more you belong to this club. Okay? So bigger masses get more perks in this club, they're attracted more with more force to other masses. Okay? Now this force is not constant, it actually gets weaker with distance too. So you have to measure the distance between the two masses, and that goes in the denominator, squared. So you see that the force of gravity is inversely proportional to the square of the separation. Inverse meaning in the denominator, and square is of course squared. So this is a particular type of proportionality that comes up a lot in physics. It's called the inverse square law. There are many physical laws that end up being inverse square laws, so we give it a special name. It's just one particular type of proportionality, right? Just like we had a linear proportionality, we call it linear or direct proportionality. This is an inverse square proportionality. So this is where we hopefully have planted the seeds for proportionalities already in homework 1. So if I said something like to triple the distance, you should be able to quickly tell me how much will the force be affected. What is it?
1/9.
1/9. Yep, that's right. So if you take the two objects and triple their separation, the force will only be 1/9 as big. 1/9 the force of attraction as before, as an example. Now when you're measuring R, you have to actually measure it very carefully. R is actually measured center to center. So it's not the nearest side to the nearest side, or something like that. You have to measure it center to center. Now Newton struggled for a while, why should it be center to center? And then discovered that maybe he should take each of these spherical shapes, and he should break them all up into little tiny chunks, and then measure the attraction between this chunk and this chunk, this chunk and this chunk, this chunk and this chunk, right? And do all the pairs until, and then he figured out that that's equivalent to just taking the entire mass and collapsing it into a point, the other mass collapsing into a point and measuring it, and those points are center to center, okay? Now there's a particular type of mathematics that is required to take an object and break it into small chunks. Does anyone know what that's called? Calculus. So calculus wasn't invented. Newton invented it because he needed it to do physics. Okay? So Newton figured out a lot of stuff. He figured out most of the stuff in this course single-handedly, just sitting by himself. Okay? Now what else is in the law? Well, right now it's incomplete. It needs one more thing. Because if you use SI units, if you put in 1 kilogram and 1 kilogram and 1 meter, you don't get a force of attraction of 1 Newton. It's not nearly that strong. And that would be a freaky coincidence if that was right, because remember, all of these things have been handpicked, right? What 1 kilogram is just arbitrarily picked by somebody at some point. Right? It's an arbitrary amount of mass that someone decided to call 1 kilogram. Same with a meter, right? Someone decided to take an arbitrary chunk of distance and call it 1 meter. So there's a constant in there called the universal gravitational constant, which is kind of like your tuning for gravity in our universe, at least our observable universe. Okay? Now, the technology was not there in Newton's time to figure out what that was, so he said, at some point when technology improves, someone should probably figure that out, okay? And someone did do that, okay? I think this was after Newton was long dead. This was the Cavendish experiment. So Cavendish got into a lab, and, to greatly simplify what he did, the essence of it was he put a 1 kilogram mass and a 1 kilogram mass, and he put them 1 meter apart, and carefully measured the extremely minute force of attraction that they have to each other. It's very hard to measure because it's so small. If you need evidence of that, you probably never put two objects on a table and come back and found them having gotten pulled together, right? Gravity is very weak. You don't notice it between everyday objects, right? So if you put that into the equation, let me clear some space here. So I have G times 1 kilogram times 1 kilogram over 1 meter squared. Oops, squared. So if you can actually measure the amount of force, then of course the one thing that remains is the universal gravitational constant. The result, let me put it over here, is 6.67 times 10 to the minus 11th newtons. Tiny, right? 0.000000667, right? Tiny. That's why when you and your friend are walking down the street, you don't notice whoosh, get pulled together, right? By gravitational force of attraction. It's a minute force. Now, if you use this, of course, you can solve for the universal gravitational constant, and the value you get is G equals 6.67 times 10 to the minus 11. Now, it's going to have some hideous units, Newton meters squared per kilogram squared. Ugly, but necessary to make the equation dimensionally consistent, right? Because what you're putting in on the right-hand side are kilograms and meters, and you need it to come out in newtons on the other side. So this is the necessary units for the universal gravitational constant. And everywhere in the observable universe, we believe that it is this value. Now, we don't call up, alien Cavendish folks on other planets. We, of course, infer the value by looking at the motions of things through a telescope. So far as we know, this is a universal value. Okay? This is a tuning constant of the force of gravity in the known universe. Okay? Cavendish was the first one to do this. Nowadays, this is a common junior level physics lab. So you can get into a lab, the technology is good enough in this day and age, where you can go into a lab as a junior with some equipment that's been provided to you, and you can measure the minute force of attraction between two masses. Okay? Are there any questions so far? Okay, so that's the law. It's a very simple law. It simply says that the force of attraction is dependent on the mass of each thing and the distance between them. I'm going to show you how this simple law produces all of these features. Okay? So let's do that. So the first thing I want to do is apply it to a common system. I'm going to apply it to the attraction of the Earth to a person. I'll call the mass of the planet mass of Earth, and I'll call the mass of the person our object of interest. We, of course, usually use lowercase m. Now, you might say, why is it that I'm picking this system to look at? Well, this is an opportunity for me to show you why the force of gravity ever amounts to anything. So, just after I finished telling you that every mass attracts every single other mass in the universe, I'm attracted to this pen, I'm attracted to that clock, I'm attracted to this Earth, I'm attracted to the sun, I'm attracted to some black hole millions of miles away, I'm attracted to every single mass in the entire universe. And yet, once I said that, I told you that the multiplier in the front, that big G, is this very, very tiny number. And so you might wonder, how is it that this force of gravity ever becomes something reasonable? So when does the force of gravity become sizable? It's not very impressive if it's there, but it's always so tiny that you don't even notice it. Well, two things have to happen in order for the force of gravity to ever have a chance to be something that's not tiny. One or both of the masses must be very large. That's one chance you have. So in the equation, if I were to write every variable according to how big it is, of course the universal gravitational constant is a tiny number. But if I multiply that by at least one giant number, then of course tiny number times huge number could be reasonably sized number, right? Correct? Okay? So that might be a sizable force of gravity. So I've somehow offset the tininess of the gravitational constant with at least one of those masses being very large. Okay? Now that's not all that has to happen, because the sun is 1,000,000 times more massive than the Earth. But I don't get pulled off the surface of the sun, or surface of the Earth, and get incinerated into the sun, right? Why is that?
Distance.
Distance. That's right. So one or both of the masses must be very large, and the distance should not be too large. Because, again, if I have a fighting chance of having the numerator be big by putting in a large mass, like say the sun, but I'm also extremely far away from it, so if I take a huge number in the denominator and square it, this force of gravity is still going to be very small. So we have to make sure that the variables in the equation are reasonably valued such that we get something that isn't a tiniest little fraction of a Newton. So of course there's only one object that gets through this sieve that satisfies both bullet points 1 and 2. A very large mass that's fairly close by. Hey, this big rock we live on, right? So the Earth. So while you feel of a force of attraction to every single other mass in the entire universe, you only commonly notice one of them. That is your attraction to the Earth. Okay? So I'm going to go ahead and draw that force. You're pulled down by the Earth is pulled up by you. It's actually a mutual attraction. Gravity is attractive. So downwards, saying you're pulled downwards toward the Earth is another way of saying you're attracted to this Earth. Okay? So let's work out the details. Question before I do that? Yeah.
So is it like the same thing as like when the moon comes closer, even though Earth is a little bit huger in mass, but the distance is somewhat close to a point?
Sorry, so the moon is doing what?
It's like closer to the Earth. That's why
the Earth will, yeah, the moon will pull harder on the Earth when the moon is closer.
Okay.
That's right. One of the effects of the moon being directly overhead is that it lifts the water up a little bit, because the water is mostly attracted to Earth, but it's a little attracted to the moon as well. So you tend to have high tide, right? So there are gravitational effects that we notice from the moon. The moon causes the tides on Earth. So let's do a slightly simpler system first. Let's just take a look at the attraction here. So what do we have? We put in the two masses, and then we have to be careful. Do I put in a distance of 0 since I'm standing on the Earth? No. What do I put in? Radius of the Earth. That's right. Remember, we have to measure center to center. Technically, the radius of the Earth plus radius of me, but my radius is negligible in comparison, right? So let's do this. I can give you the radius of the Earth. The radius of the Earth, I'll put it in your notes right now, it is also available on the equation sheet, is 6.38 times 10 to the 6th meters. Now, how is that known? Well, of course, that's just measuring the properties of the Earth, right? The whole idea of people thinking the Earth was flat, that is a little bit of an urban legend. There were certainly some people who thought that, but it's been known well in BC times that the Earth is round. For instance, if you were in a country where they often sailed ships, you could just watch someone sailing their ship away, and you'd notice that the last thing you'd see is the mast disappearing past the horizon. People have known for a long time that the world is round. In fact, the first measurement of the radius of the Earth was done in BC times. So this was first measured in BC times by Eratosthenes. Eratosthenes. Now, he didn't just walk around the entire Earth counting steps. He was a little more clever than that. He was basically the modern equivalent of what we now call time zones. You guys probably know it's 3 hours later right now on the East Coast, right?
Yes.
Okay. So the sun's going to go down there first.
Yes.
Okay. So you can use that same principle to basically measure the radius of the Earth. What he did was he planted a stick, and of course, at noon, in that location, it's not going to cast a shadow, right?
Yes.
Sun's directly overhead. But somewhere else, it will cast a shadow, right? Now, if you know the distance between those two sticks, and you also know the difference in their angle, you can, of course, work from how much distance would you have to walk in order to make the stick rotate 360 degrees, right? So you can measure the circumference and then work to the radius, right? That's not a hard thing to do. You just have to be very careful in your geometric calculations, right? And you have to make sure you know how far apart the sticks are. In BC times, he got the answer right. I think it was within 10%. Some of your labs, you're lucky to get 10% error, right? So that's the radius of the Earth. How about the mass? The mass of the Earth is 5.97 times 10 to the 24th kg. You might similarly ask, how do you do that? How do you get the mass of the Earth? I'll come back to that in just a second. So, now that we have these things, we can calculate the force of gravity that is attracting you to the Earth. Now, just for convenience sake, everybody in this room might have a different mass, right? But everybody is feeling the pull from the same object. The predominant pull you're experiencing is from the Earth, right? So it might be convenient to package these all up into a common value just so that then we can all multiply our own masses in, right? So we put in the mass of our planet, the radius of our planet, universal gravitational constant. And if you plug in the numbers, this, and the universal constant, you will get 9.8 meters per second squared in number and unit, which is pretty familiar, right? In fact, that's the abbreviation we've been previously calling g, little g. So we now know where does our value for 9.8 meters per second squared come from. G at the surface of Earth comes from this expression. So if we go back over to our checklist, that is certainly a constant acceleration in the sense that the mass of the object itself does not factor in. How did it come out to be the same for everybody? Well, we said before that if the acceleration is going to be the same for everybody, how does the force of gravity know to pull harder on bigger masses? That's inherent in the law, right? If a mass is larger, it's a larger participant in the gravity club. So gravity will proportionally pull harder on bigger masses so that they feel exactly the same acceleration as everybody else. Okay? How does gravity know to pull harder? This mass is a bigger member of the gravity club. So why is it that when the mass is larger, the force is larger? That's inherent. Because it's the same mass which measures your stubbornness that also measures your participation in the gravity club. So yes, if you're more stubborn, you're harder to pull, but gravity pulls you harder because you have more mass too. Why is the value 9.8 meters per second squared? We just saw it come out of the equation. Why is it downwards? Gravity is attractive. Why does it have to be the Earth? Obviously, it depends on the mass of the rock we live on. Why do you have to be near the surface? Because the center-to-center distance is important. So all of the features of gravity that we previously just kind of used without knowing why, it comes out of this single equation. Okay? Are there any questions so far? Yeah?
How can you prove it downwards?
How can I prove that what?
Downwards from
Oh, downwards because gravity is attractive. Earth's below you, right? So it's going to pull you down.
remember those variables, G and B.
Well, this is just the size. The force I've also given you is attractive, right? So this is just the numbers part. We also know that separately that the gravity is attractive. Now, for full disclosure, you may notice I kind of glossed over what's the mass of the Earth. We kind of put the cart before the horse here. What really happened is that Cavendish measured the big G, Eratosthenes measured the radius of the Earth, and others after him that made refined measurements. Just like you guys, dropping an object, you can measure the local acceleration, right? Like you guys did in your lab?
Yes.
So in fact, the mass of the Earth was measured here. That was the Earth, mass of the Earth has been determined by this formula. Okay? So that's really what Cavendish was after. He was after not the universal gravitational constant at all, except as a means to an end. His ultimate goal at the time was to figure out what's the mass of our planet. Why did he want the mass? Well, taking the mass of the volume gives its density. Why did Cavendish want the density? No one had any idea what was going on inside the Earth. So measuring the density might give you a clue what it's made out of. Now you might say, well, how do we know that this value is right? If the theory gives us the value, maybe the theory is wrong. So maybe the theory is wrong and the mass of the Earth is wrong. Well, to that I can only say there are an incredibly large amount of corroborating pieces of evidence, right? So at this point in time, we've looked at many systems and seen that this all works, and this is correct. So basically right here, this gives us a roadmap of how to find the gravitational acceleration in other places. So for instance, maybe you wanted to find the g at some very large distance above the Earth. Well, then let's just leave the denominator floating so that we can put in whatever r value we want. Now, don't get me wrong, if you're going a few meters one way or the other, right? Maybe you're even flying in an airplane at, 10,000 meters or something. 10,000 meters is a drop in the bucket of 6 million. So we really got to get up there. We're definitely going to need a space helmet of some kind because you will definitely be way above the atmosphere. And then you could figure out the g value up there. We could say things like this, right? If the value goes from the radius of the Earth to, I don't know, let's go up to 3 radii, then what is the change to the gravitational acceleration? 1/9, right? It's still an inverse square law. The force was an inverse square law, so is the acceleration that results. So this will be 1/9 of the value at the surface. It'll go from g surface to 1/9 g surface. So that would be roughly what? 1 or so? 9.8 over 9. Let's call it 1 just because I don't have the number handy. So up here, g is approximately 1 meter per second squared. It does get weaker as you go up. Now, when I say go up, if you're climbing the top of Mount Everest and you're near the top and you fall off a cliff, it doesn't mean you'll come smoothly to a stop. It's small consolation that the acceleration, instead of being 9.8 meters per second squared, it might be 9.79 meters per second squared. You might die a nanosecond later, okay? You really have to get up there. The distance here is now 3 Earth radii. Remember, it's always center to center. So you've increased the center to center distance from 1 to 3 Earth radii, which means, by the way, you are 2 Earth radii away from the surface. You could fit a whole other Earth between you and the Earth, right? You're way up there, okay? So the acceleration, the force of gravity and the acceleration it causes does diminish, but it diminishes so slowly that it's not really constant, okay? So it's just approximately constant if we don't go too far, okay? This gives us a prescription, by the way, now that we know what the gravitational acceleration is near Earth, we can swap in any planet, okay? Or let's say the moon, right? If we want to go to the moon, g surface will now be a different value simply because you're standing on a different rock of a different size. We could just go put in the mass of the moon and the radius of the moon. So the Earth doesn't have any special powers of attracting things. All masses attract all of their masses, and when those masses get big and you get very close, you start to notice. So whatever cosmic coincidence led the Earth to have its composition, its mass, and its size, the moon has a different one. If you worked it out, it would be about 1.7 meters per second squared, which is about 1/5 of Earth's. And of course, if you're planning to send up a moon lander, you should probably have some idea of what they will expect when they get there. Of course, they calculated it in advance and they were right on the money. They realized that the gravitational acceleration there was going to be a lot less, and so the spacesuits that they designed are several hundred pounds of life support equipment. It's very difficult to walk in one of those spacesuits on Earth. But that's not what they're designed for. They're designed for walking around on the moon, where the gravitational force and acceleration are much weaker. In fact, when the astronauts first got up there, the gravity was so weak that when they would step, they would accidentally push themselves so high in the air that when they went to step down, they would actually miss the ground because they hadn't landed yet. And they found it was a lot easier to hop along, like bunny hopping with 2 feet. Okay? So this gives you the prescription to find the gravitational acceleration anywhere you want. You just need to know the properties of the thing you're standing on. You need to know something about its mass and its radius. You can find it at the surface of Earth, and of course we already knew that value because that's where we are, so we measured it in the lab. We can find it high above the surface of Earth. We can find it on the surface of the moon. You can find it high above the surface of the moon, or Pluto, or wherever you want, right? You can find it. Now that we know the universal theory, we're not limited to experimental evidence of being able to use this particular G value. Are there any questions on that? Okay, so let's talk about now the difference between mass and weight. Mass versus weight. Two things that are used interchangeably in everyday language, and that is because people don't necessarily understand that they're very different things. So let's talk about that. Mass is what we call an intrinsic property. Intrinsic means that it belongs to that thing itself. It's a part of that thing. So that it's a property of that object that's indistinguishable from the object itself. It's how much stuff there is to the object. So if you have a 1 kilogram mass, it's 1 kilogram no matter where you take it. You take it to the surface of the moon or the earth or anywhere, 1 kilogram is 1 kilogram is 1 kilogram. Now that's to contrast with weight, which we call an extrinsic property, which means that you can't really define the weight of an object without talking about it in reference to another separate object. The weight is another name for the force of gravity on the object. But remember that that force of gravity on an object comes from another object. From another object. For example, the Earth. So you can't really say what the weight of an object is until you say the weight on what planet, right? So the relationship between the two, the force of gravity, also known as the weight, is equal to mg. So notice when you want to find the weight, you multiply the intrinsic property of how much mass something has by the local gravity, which is created by, of course, the other object. Okay, or the mutual attraction of this object to the other object, the planet or whatever. Now don't get me wrong, if this g is fixed by your location, if you have more mass, if you have more intrinsic stuff to you, you will weigh more. It's right in the equation. More mass is more weight. If you have more stuff to you, then you'll be pulled harder by the Earth. If you have more mass, you'll weigh more. If you weigh more, you have more mass, and before long, people are not distinguishing them at all. And mass gets blurred with weight. Because if one is bigger, so is the other. However, what I am aiming to do now is to show you how you can gain mass and lose weight. Let's talk about that. So I have the Earth here, standing on the Earth. I have my space helmet on, which is going to give you a hint. I'm going somewhere. Okay? I'm going to the moon. And my trip to the moon will take a while. I'm going to be cooped up in my spacecraft, and I'm only going to bring junk food with me. I'm going to eat the worst food I possibly can. It's a long trip, and I'd just like to eat Twinkies and crap like that while I'm on my journey. And I get there looking a little more like this. Okay? So there is definitely more stuff to me. I have gained mass, okay? Now I can gain mass, but I would be hard pressed to arrive 5 times more massive than I left, right? You gotta really put down the junk food for that, okay? But I'm also going somewhere where the G is 1/5 of the value where I left. So maybe a little bit of elevated mass multiplied by a much, much smaller local G value, I've actually lost weight. It seems like cheating, doesn't it, right? Because weight is defined by what's pulling on you. So if you don't like your mass, go somewhere where what's doing the pulling is different. Switch it out from the Earth to the moon. I've gained mass and lost weight. I've gone somewhere where even if I have gained mass, the thing that's pulling on me is not pulling on me as hard. That's what weight is. It's the force of gravity on you. Now what makes this even more confusing is when you get into the units. So let's talk about the units of this stuff. So let's talk about the units of mass and the units of weight. Let's talk SI first, as we usually do, but then I'm going to put the English system unit here as well. Now you guys should be able to tell me the SI units. What do we use for mass in SI?
Kilograms.
Kilograms. What do we use for weight and all other forces?
Newtons.
Newtons. Okay. Now let's go to the English. What is the English system unit for mass? Slugs. Okay.
Okay.
Ever heard of a slug?
Nope.
No. That's because we're in this unique position in this country where we sort of use English system, right? Feet, miles. But we also live in a world that almost exclusively uses metric, so we're more likely to have heard of a kilogram than a slug. Where does pounds go? Pounds is actually over here. Pounds is a unit of force. And so the two things we commonly use in everyday language are actually going across categories. Okay? Kilograms is a measure of mass, and pounds is a measure of weight. So if we go over here, in our trip to the moon, we have gained kilograms. This diet plan would be very disappointing for Europeans, right? You said I'd be less kilos. Well, you're the same amount of kilos, or you're the more kilos than when you left, okay? But you have lost pounds. So you can gain kilograms and lose pounds because they're measuring different things. And so in conclusion, we can now understand what I said on the first day of class. I was trying to get you a little flavor of how much a kilogram was, and I said 2.2 pounds, but I put a big asterisk there and said not always. This is on surface of Earth. On surface of Earth. What this is basically saying is 1 kilogram of mass weighs 2.2 pounds on Earth. That's how much the Earth pulls on 1 kilogram of mass is 2.2 pounds of force. We, of course, don't use pounds. Usually we use newtons. This would be 9.8 newtons. These are equivalent amounts of force. 2.2 pounds and 9.8 newtons are force. This exact 1 kilogram of mass will weigh whatever weighs 1/5 of that on the moon. So the 2 point, you'd have to divide these two both by 1/5. So 1 kilogram is not always 2.2 pounds because it's an extrinsic property when you talk about pounds. It's what's doing the pulling. If you're through this 1 kilogram mass into deep space, it would weigh 0 newtons or 0 pounds. Okay? So that's it for today. We'll pick up some new stuff next time.